Good morning. Welcome to this video on the topic of work power energy and simple harmonic motion. So this is a problem in front of you which has two concepts involved. One is a concept of simple harmonic motion, especially the energy equation of a simple harmonic motion, and of course, the concept of potential energy, conservative force. All of that is included in this. Why I say so? Because it's a linear simple harmonic motion, and the spring force or the restoring force which you see is a conservative force. And I will go deep inside this problem, but I just want to give you a heads up on the way we are approaching this problem is from the point of view of one law of conservation of energy. And you know by now that the second thing is what are conservative forces. Third, you must also know what is the concept of simple harmonic motion. And you may not have reached the topic of simple harmonic motion, but without that also, if you have studied spring in the chapter of work power energy in NCERT, for example, they have explained a conservative force, which is a spring force, and the potential energy associated with motion of a body attached to a spring. So even if you understand that, you should be able to solve this. And without further ado, I will just go and start solving this now. But before I solve this, I told you my unique proposition is I explain what is going on in the situation. Once we are clear on the concept, then we go and solve the problem. If I just write the solution for you, you will not gain anything from me. If I explain you what is happening, you're likely to be able to get your logic strengthened and be able to solve even complex problems. So I will first explain you what is happening through the concept building, and then the second part of the video or the lesson, we will then go and solve this problem using the concepts we build throughout the concept building phase or the first part of the lesson. So let's get started on this. Thank you. All right, so let's start building the concepts which will be useful to solve problems like these. Okay, and I will start with the concept of a drawing. Let's look into the situation as I. So this is your floor, this is your spring, okay, and the spring is then connected to a mass. Okay, this is your mass. Okay, the mass is connected to a spring with a spring constant of K, which is given in the numerical, right? Spring constant means what is the restoring force per unit meter which gets generated when the spring is either pulled or it is compressed, right? So every spring, if you have a spring like this, you compress it, right? It will push you back. Now this pushback force, this push back force here, push back force per meter is fixed for a spring and is called as the spring constant K. Okay, it's called a spring constant. I will just write it as spring constant. Similarly, if you take the spring, it is at the position where it is neither compressed nor elongated. Now what you do is you elongate it. So this is a mean position. This was compression, this is elongation. Now this spring becomes longer. Okay, we draw a long spring. So I started pulling it from here. Now this is the extra elongation in the spring. This is the spring which has got elongated. Now this spring will pull you back. Okay, earlier it was a push back, now it's a pull back. It will try to pull you back to the mean position from where it was neither compressed nor elongated. So it will pull you back. You can feel it in your hand, right? The force it generates to pull you back, the force it generates to pull you back per meter length of the spring is called as a spring constant, K. So these two are one and the same thing. You can either pull the spring or you can push the spring. The force generated, this force is popularly called as restoring force of the spring. Okay, I hope this is making sense to you. This is one thing you need to do. Every spring, when pulled or pushed, generates a pushback and a pullback force, which is measured per meter basis. That is called as a restoring force of the spring. Now, so one concept is this: you must know the behavior of the spring, as it is pulled and or it's compressed. Let's talk about another situation. So you have a spring. It is right now in the neutral position. A neutral position is where the spring is lying as is. There is neither any pull nor push. This is your situation number A. Okay, now I call this it is lying peacefully. Nobody's pulling it. Nobody's doing anything to it. In the situation number 2, so it is at the mean position. Let's call the mean position is equal to A, and then someone comes and pulls it by a certain amount. Say it is pulled by a certain amount. It was here, and now it is pulled by a certain amount, and it reaches here, which means it is moved by a displacement. Let's call it A. This is A, right? The new position, and this was the initial position. X is equal to 0. Now, when it is pulled like this, right? This is what happens at the end of pulling, which is this is the end, right? This is a final position. What you're doing is the spring gets elongated, right? So it generates a restoring force, which is measured like kx, and negative sign means it's going to be opposite of the displacement. Your displacement is in this direction. The spring is wanting to come back to its mean position. I call this the mean position. Okay, the energy of the spring, right, at this point of time when it is pulled through a displacement will be half k. It's generally at any point in between, it's half kx square, but since your x is equal to A is the amplitude, the highest pull you have done. So this is your amplitude, okay? So x is equal to amplitude. E at the extreme end, right? This is the extreme end, the final position where you're taking it to, it will become half ka square. This is nothing but the maximum potential energy that gets stored in the spring. You must understand this, that if you pull a spring, generally the potential energy in a spring, if you remember, is half kx square. But since your x is equal to A, you're at the extreme position. I'm calling this A as the extreme position. This is half k A square. This is potential energy, highest potential energy. Okay, so I will call it maximum, right? The other key feature when the body is at the extreme position is that the velocity of the body is 0. Okay, so the total energy of the body at the extreme position is half k a square plus the kinetic energy, which is half mv square. Velocity is 0 when x is equal to a, because right now it is at the extreme position. It will not move. It is being held here. So it is equal to half k a square plus half m into 0 square is equal to half k a square. This is the total energy, right? This total energy is the maximum potential energy being held inside the spring at the extreme position. So this was a situation of elongation. Okay, now at this point there is another parameter, which is the force. So we have understood that at this point there is no kinetic energy, there is maximum potential energy, right? This is, so kinetic energy is 0 because velocity is 0, and the restoring force, which I started with, right, x is equal to A is highest minus k into A. So you have maximum restoring force. So at this point of time the spring is wanting to come back badly. So this is a point of turning. If you look into the problem today, which I have shown initial part of the lesson, it says the body wants to come back at x is equal to plus minus 2. So these are the extreme points. This is the amplitude point, so to say, where the body wants to come back it's a point of turn back. Okay, so whenever you have a body where x is equal to a, the body is at the point of turning back. It wants to, go back to its initial position, turning back. Okay, let me write it as turning back. So you are here, at this point, which is your final position. You want to turn back because the restoring force is so high. You want to go back at the initial equilibrium state. This is your equilibrium state, right? And this is your, when you're pulled maximum, right? So your force is highest. So this is maximum force. So if you elongate a spring by an amount A, the force is highest. It's the restoring force I'm referring to. The potential energy stored in the spring is highest. Okay, the kinetic energy in the spring is zero. The of the mass is zero because the 100% of the energy velocity is zero. 100% of the energy is potential now. Why I say that? Because one thing I skipped was that if you have a spring mass system which is moving like a linear simple harmonic motion, it is going here and then here. Generally, at any point in middle of 0 to a or 0 to minus a, the total energy is given by the kinetic energy of the block, which is half mv square plus half kx square, which is the potential energy that gets stored in the spring. So this is half mv square plus half k x squared. This is the total energy of a body in simple linear harmonic motion, and the restoring force is a conservative force. So there is no friction here. Okay, no friction here. If there is a friction, then these oscillations will become damped oscillation. You can see my playlist on simple harmonic motion. It explains all types of simple harmonic motions beautifully. Go through each video to get a good grasp on simple harmonic motion. If you understand work power energy, if you understand simple harmonic motion well, combine these two and you should be able to solve a lot of SHM and work power energy questions pretty smoothly. I hope this elongation part was clear to you. Similarly, what happens is, if you have a situation, where the spring is here and then you compress it and you bring it here, right? So this is the initial position. You compress it with minus A. Whatever is the elongation on this side is the compression on this side. Same equations hold. Now the spring wants to come back again. So if you look into the problem, it says the spring wants to turn back. So this is again a turn back because it is at the highest amplitude of its oscillation. It can go from it goes till A, then it comes back, crosses the mean position, reaches the highest oscillation, and then again comes back. So this is the mean position, this is the amplitude, and this is the minus amplitude. Okay, I hope this is making sense to you. So this is the amplitude, this is the minus amplitude, and the body again at the highest amplitude wants to come back. So this keeps on repeating because there is no loss of energy. The body keeps on oscillating, right? It keeps on oscillating infinitely. It keeps on oscillating, and the motion continues. So it's a conservative force. The spring force or the restoring force, which I mentioned, is a restoring force. It's a conservative force. So all the equations. It is the potential energy at the highest compression of x is equal to a. The potential energy is half k a square. Velocity is 0. The restoring force is highest. X is equal to a. Kinetic energy is 0, obviously, because the velocity is 0. So all of this is applicable anyways, right? I hope this is making sense. We are at the compression stage. Now let's talk about this particular stage, right, where equilibrium. So I talked about elongation. I talked about compression. So this was compression state number 2. Now I will go and give you the state number 3, where you're at the mean position. Now you're coming back after compression and elongation. So this is your spring. This is your spring, and the spring is here, and then of course you have a block, frictionless again. Now when the spring went this side, it got elongated, then it got compressed, it went this side, it is back here. At this point, the elongation is 0. Here the elongation was A, here the compression was A, here it is 0. What is happening to the total energy, right? Total energy is equal to half mv square plus half kx square. I haven't done the derivation of this in this video, but you can go and check my playlist on simple harmonic motion. Also go through work power energy chapter, conservative forces, where spring energy has been explained in NCERT. Half kx square, x is equal to 0. So the total energy at this point of time is completely kinetic, is equal to half mv maximum square. So at the equilibrium position, the velocity is maximum. All the energy is kinetic in nature. Here at the extreme positions, all the energy is potential energy. Potential energy, potential energy, potential energy. At this point, the energy is kinetic energy, right? So the energy is conserved. It's a conservative force situation. Either it gets converted purely into potential energy, or at the medium point or the equilibrium point, it is absolutely in the form of the kinetic energy only. And what happens to an interim point, which is between the equilibrium and the maximum elongation, or equilibrium and compression? Any point here, for example, here, the total energy here is given by half mv square plus half k x squared, right? So x is known to you. What is the position, by which the body has moved, on either side? Put it there. You have the total energy. You can find the velocity of the body there, right? So remember, this is a general formula. What I did was I calculated all of this at extreme positions and at equilibrium position. Now at the equilibrium position, there is no restoring force, okay? Because x is equal to 0. You're not pulling or you're compressing. So F is equal to 0 means F is equal to the restoring force is 0. It's Kx, right? K into X, restoring force with a negative sign. X is equal to 0 because you're at equilibrium, and therefore you have no restoring force here. Make sense? So here the body has no urge to turn back. The turning back happens here and here because the maximum elongation is there. The maximum restoring force is here, and therefore the body wants to go back here, right? The body wants to go back here. So just be very careful that when you read these questions, the point of turning back is clear in your mind. The whole spring action, let me just take you to the question, right? It says the body wants to turn back. The body. So turning back, should raise an alarm in your mind, and you should know that we are talking about an extreme position here, right? So the body has probably moved to extreme positions of elongation and compression, and therefore the restoring force is the highest, and therefore the body wants to turn back. I hope the meaning of the word turn back is clear. At the point of turn back, what happens? The potential energy is highest, and the whole energy actually is potential energy. So this 1 joule will be completely potential energy. There will be no component of kinetic energy here, right? You need to prove that this is the point of x is equal to plus minus 2 meters. It's a turn back point. So at the turn back point, it is very important. The turn back point is the extreme points of oscillation as in simple harmonic motion. Extreme points of are these extreme points where the body wants to come back. So this is equilibrium. It gets elongated. It reaches here, right? This is the point of turn back. It is the extreme. The whole energy has got stored as potential energy here. Then it comes back, crosses, and it reaches the other extreme. Again, a turn back is there, right? Turn back urge is there. It wants to go back because the spring wants to pull it back to the original position, which is this. Here it is elongation side, elongation, which we discussed in detail below. This is the case of compression, right? This is the case of compression, right? It again wants to go back, and hence +2 and -2, both situations are applicable. You can see any video on this topic or any solution on YouTube. There is no explanation given. Explanation in physics is very important. Explanation. If you don't have explanation, there is no physics. Just giving merely solutions doesn't help anyone, right? Now we are armed with the knowledge of simple harmonic motion. We understand it's a conservative force. No energy is getting lost. It is only getting converted from kinetic to potential, potential to kinetic at the middle point. Or the energy remains conserved, but it gets stored in the form of kinetic energy and potential energy everywhere. So let's get going on this and let's solve this problem now and see what is the way to approach this. So I will just delete all of this so that it's easier for me to write and easier for you to see what all is written, and you can look at it more clearly. Okay, I'll just delete this part also. It's recorded so you can always see this. Alrighty, so I have highlighted some major points. Now we have good concept grounding, right? We understand the whole concept as to what's happening. There is definitely law of conservation of energy. It's conservative force. There is definitely involvement of simple harmonic motion. We understand the point of turn back. So let's say this body, the total energy of this body is half k x squared plus half mv squared. The total energy is known to you, right? So it's 1 joule. At the point of turn back, what is the velocity? 0, right? If you go back, at the point of turn back, velocity is 0. It is the extreme point where the velocity is 0, right? Velocity is highest at the equilibrium position. This, right? Where it is, you pull it, here the potential energy is highest, it comes back, here the kinetic energy is the highest. So velocity is 0 here. So this is what I'm going to do, half k x squared, because I know it's a point of turn back. So it's a point of turn back means velocity has to be 0. So the kinetic energy here becomes 0. So 1 is equal to half into 0.5 into x squared. X squared is equal to 2 divided by 0.5. X squared is equal to 4. X is equal to plus minus 2 meter, right? This is exactly. So at the, what are the turn back points when x is equal to plus minus 2, which means this is 2 meters, and on the other side when you compressed it, it is minus 2 meters, right? So it was very important that you understand turn back, what happens there. Why turn back? Because the restoring force is highest at these points. The spring is pulling back the mass, wants to take it back to the the equilibrium position, and same is true here. It wants to take it back to the equilibrium position. So an oscillation is like this. It starts from here, goes like this, comes back, and then it comes back. Here the velocity is highest when it is coming back. Here the velocity is 0. Again the velocity is 0 at the extreme end. This is the equilibrium point. Here the velocity is maximum. The turn back points are these. Turn back. Turn back means the potential energy is what it is. There is no kinetic energy, and therefore I completely removed this. I completely changed the total energy into potential energy only, and I was able to get the point of turn backs. My channel has 2,500 videos. Please go and watch every video. Some of the videos are very short, brief, concept oriented. Build your concept. Do not waste time on just looking at solutions. Nobody gets helped by looking at solution. Solution did not teach you anything. Go and watch solution of this particular problem on any website, anywhere. Nobody has given any detailed explanation. It is just addiction. You don't learn anything from solutions. Always learn physics from the point of view of understanding, is what I'm urging you to do. Do not forget to subscribe to my channel, because the quality of questions and the explanation will help you build concepts to a level where you can crack any examination in the world. You may be a student of AP Physics, you can be a student of CBSE, you can be a student of ICSE, you can be a student of International IB Board, you can be a student of CBSE or State Board, or you're a student of NEET, or you're a student of JEE Mains. All these videos which I've built are very concept oriented, very solid explanations have been given, very simple explanations have been given, which are not available to you in any other channel. So don't forget to subscribe. Wait for my next video. One more beautiful numerical coming your way to help you improve your life. My aim is to help at least 1 million students, get strong in physics and build careers. If you're able to build career, it will bring a lot of happiness and prosperity in your families. That's my aim. I want at least 1 million students to benefit from this channel. I am doing all of this free of cost. Please encourage me. Please share the link of my video channels in your family circle with your uncles. People should subscribe to this. This should be the quality channel which should be looked at for quality solutions and explanation by any decent student. If you're a student who is not interested, who's just looking at some quick fix, it's a wrong channel. But if you're a student deeply interested in building career, bringing happiness and prosperity to your family with the help of education, from a good college, this channel will help you get that admission because of the quality of explanation. And in fact, if you become a medical student, you become a physicist, or you become an engineer, you will see that this channel has questions even for engineering student, the first year of engineering, or for that matter medical. The physics you need to be able to solve real world problems has also been taken into account. Obviously the level is class 11, 12 and competitive examination, but still the quality will you can I can vouch for the quality of solutions. So with that, I will bring an end to this video, and thank you very much for your attention. Wait for my next video. Do not forget to subscribe to my channel. Thank you very much.